Welcome to lecture number 13, and we started discussing on hysteresis loss, uh, why it takes place, some physical reasoning only I gave. And now, to understand why hysteresis loss takes place, we have understood something. Then we will try to see on what factors it will depend, as we did in case of eddy current loss. But before that, I have told about the BH characteristics of a magnetic material. Okay. Suppose you have a magnetic circuit like this. Okay. Let it be like this, it does not matter. Acha. And you have a coil wound over it, exciting coil. Here I will pass current I, function of time. Now, so far I have drawn the BH characteristics. Generally it will be like this. This is H, which is equal to N I by L. L is the mean length of the flux path. This we know, and this is your B. Now, this is how I draw, and if you increase this current I starting from 0, initially it was not magnetized. So, as I go on increasing the current, you will find B is increasing almost linearly in the initial phase. Then after some time it becomes saturated, that is further increase in H here will not cause practically any increase in B. The reason once again is we can understand the tiny magnets which are north, south, etc. As you are increasing H external magnetizing force, you are forcing the tiny magnets to be aligned in a particular direction. And after all the magnets are aligned, okay, south north like that, whatever way, then further increase in H, what further to align? Everybody has become a disciplined soldier and they are in line. That is why this saturation zone takes place. That way you can think. Now, suppose I am increasing the value of H, but this we will see that what is the effect of hysteresis. As you go on increasing the current, B increases starting from 0, it goes like this here. Before I tell you about that hysteresis loss or hysteresis loop, let us try to understand one important thing, because I have to after all estimate the hysteresis loss. Suppose this coil, this current is increased from 0 value to a particular value, here say some value I. This axis can be treated also as current H or current, because N, L are constant. Suppose you have increased the value of the current I. As you have increased, how much energy I have supplied to the coil, that I want to study. Since this current you have increased from 0 to capital I or 0 to some H, which is to be multiplied by N. So, N I by L, this H value, I want to know how much energy I have supplied. First of all, have I supplied any energy to it? The answer is yes. See, because of the fact this is the coil, I am increasing the current here. Therefore, flux linking with the coil is changing, gradually increasing. Therefore, it will become a seat of EMF just like transformer plus minus E, and it will try to oppose the cause. What is the cause? Because current was increasing. So, its polarity will be such that if this induced voltage is allowed to act, it will try to reduce the value of the current. That is why we got plus minus. Now, in circuit, any circuit, if an element has a voltage across it of this polarity, if current is entering through the positive terminal of that element, then we say it is absorbing energy, as in the case of charging a battery. To the plus terminal of the battery, you have to inject current, then only battery gets charged. So, energy will be absorbed, and voltage across this coil. So, how much energy is absorbed in the process when I increase the current from 0 ampere to some capital I ampere. Okay, that is the goal of the first part. Okay, what I will do is this: as I is increasing during this process, I is a function of time, you know. So, induced voltage at any instant, suppose the current is N I by L, okay, and the B value is B. So, and then the induced voltage will be N d phi dt, d dt of phi, phi is B into A is the cross sectional area, is it, N d phi dt. This is the voltage, and the polarity I have taken Lentz's law into account. Do not be under the confusion that minus n I have written, okay, n dBA dt is positive and polarity I have very correctly put on this diagram. So, this is the induced voltage. Therefore, instantaneous power absorbed by the coil, this I am just writing dP. Why dP? P, instantaneous power absorbed by the coil will be N, A is constant, dB dt. Why A is constant? A is the cross sectional area, B is changing. So, at any instant this is B. Okay. So, N A dB dt. Then energy supplied. So, what I am essentially doing is, let me write it like this: at time t, current is I. At time t plus dt, which means a particular H, a particular B. At time t plus dt, suppose some time elapses, current has I have increased from I to di. So, that H has increased from H to dH and B has increased from B to dB. And all these changes have taken place over a time interval dt, and that dt I can assume to be very small. So, B, it has become B plus dV. Here it was N I by L, this point is N I plus d I by L and so on. So, this is dH, is not, this is dH. Therefore, this is how things are going. Therefore, in time dt, energy supplied, I will write in black, energy supplied, energy absorbed by the coil in time dt, in time dt will be simply p into dt, and that will be equal to n a dB dt into dt. This is the thing. So, P is this into I, correct. Power is voltage into current. So, here there is current. This will be the thing. Acha. This dt can be struck off and you will be left with n I a dB dt. Is not? Then what sorry, dt is not there, dt has already gone, n I a dB, and then what you do, you multiply this with this mean length of the magnetic circuit L. So, multiply and divide. So, you will be getting n I by L dB into A into L. This is what you will get. AL becomes the volume of the core material, cross sectional area into the length, average length. So, this is volume of the core material. This will be the case. So, energy supplied during this time. So, P dt then becomes equal to H into dB into volume. That will be the case. But what is H into dB? H into dB is nothing but this area. This area is this H into dB. So, as you have increased the current from I to I plus di or H from H to H plus dH, this is dH, this one, energy absorbed by the coil has become H into dB. Therefore, what is the total energy supplied then? Total energy supplied to whom? Supplied to this circuit, to this magnetic circuit, to the magnetic circuit, as you have increased the current as I changes from 0 to some value capital I, that is up to this point, will be nothing but this whole area. Are you getting this whole area now? H dB, this strips you have to add. So, this area. So, if I write it 0 some A, this point let us call A C, then as total energy supplied to the magnetic circuit as I changes from 0 to I will be equal to area O A C O. This is the area, shaded area, that much energy we have supplied. This will be utilized to find out more about hysteresis loss in the next one. So, what I will do is this, I will simply draw this coil now, but in my mind it is there, it is wound on a core material things like that. And here I will draw the BH curve. So, what we have seen, as I increase the current, it will go like this. So, BH curve. Now, the game starts about hysteresis loss. Suppose I am increasing the current to this value. So, this axis can be treated as H or I. Suppose you have increased the current to a level of I max, and this axis is your B, and suppose it reaches some B max. Okay. What is this I? This I is here. This is the coil having number of turns n. It will be like this. Now, for the first time when I am doing, let us imagine that this current I will make it AC, sinusoidal current. So, current starts rising, current increases with time. Suppose I say, let me draw that current waveform also in this axis. This is I, this is I max, and here it will be minus I max. So, suppose current is moving like this, and this axis is your omega t. The variation of current against time, sinusoidal suppose. So, current increases from 0, it reaches maximum, at that time it is V max. After this, current decreases, this current I t, which is sinusoidally varying, sinusoidal current, sinusoidal time varying current. Suppose now, after this, the moment current starts decreasing, the BH curve does not trace back the same path through which it went. It will be in fact doing like this now. This is while current was increasing, it will go like this, but while tracing back, when we are decreasing the current, it will follow another path above this. That is, the molecules will be sluggish. After they have reached that, you are applying a negative H, then they will follow that instruction, they will try to follow, but in a sluggish manner, and this is called hysteresis. It will lag behind. Okay. The way they went up while you are decreasing H, it will be sluggish, sort of inertia or whatever it is you call. It will go like this. So, this is your pi by 2 and this is pi. So, between 0 to pi by 2 it went like this. Then from pi by 2 to pi, current has become 0, but you will find it has come here. And even when H has become 0, it is having some field retained, and it is called residual field, residual field. If somebody stops everything here, it comes here, only one pulse of current passes. You will find this iron piece will become a sort of permanent magnet retentivity, and it will have a residual field like this. This positive pulse of the current, let us talk about. Okay. When the current increased from 0 to I max, how much energy I have supplied to the coil? I know the energy supplied to the coil is the area between this curve and the ordinate, h dB, integral h dB into volume, is not energy supplied. So, as the current increased from 0 to I max, energy you have supplied is nothing but this area. This whole area, the pink shaded. During this to this part, pi by 2 to pi. So, during 0 to omega t to pi by 2, I was positive and increasing, is not. So, during this zone, if you draw the coil, this is I was increasing and positive, the induced voltage must have been like this, plus minus, this is the induced voltage, and current is really positive. So, it was absorbing power, and what is the amount of power that it has supplied? If I call it 0, if I give them name, this point, suppose some name I give A, this point is C, this point is D and O. So, I will say energy absorbed during this interval, energy absorbed is the area, which area? 0, A, C and D and O, back to O, this whole area. During this interval, what is happening? Omega t, pi, and this is pi by 2. During this interval, I is still positive, no doubt, but I is decreasing, d I dt is negative. Therefore, or dB dt is negative. Therefore, polarity of the induced voltage has reversed here. What this coil is doing now? It is then delivering power to whom? To the source. Earlier it was absorbing power between 0 to pi by 2, this region d I dt positive, it was absorbing power from the source. Now, it will give back power to the source. So, power is returned during this interval, power is power or energy, power, energy is returned to the source, energy is returned to the source, because polarity has decreased. Now, the question is which area gives me the energy? Okay, this is now your BH curve. You do not have to take this, because now when you are decreasing current, as I told you, because of hysteresis, the BH curve will be traced by this path. Therefore, area enclosed by this and this y axis gives you the energy enclosed, and this area is this area. This blue hatched area, if you call this point as P, energy is returned to the source and must be given by the area P C d P, P C d P, is it P C d P, this area. Therefore, during 0 to pi by 2 we supplied so much area, but while the material was having reduced value of B tracing back here, when you are decreasing the current, the an amount of energy returned is less. This must be understood per unit volume. So, let us go to the next page, and let me now draw this once again. So, here was my coil, mind you it is wound on a magnetic circuit, we are not drawing. Now, what I will do is this, what I have done last time, let me do it like this. So, this was the BH curve, which I will draw with this color. And while tracing back here, it will be like this. So, this is my positive direction of I, but suppose this I is I max sin omega t, suppose this current is this, then I also draw the current. I can always draw current. This is my omega t axis, variation of current I am showing. This axis, as I told you, can be treated H or I. This is your I max, and this was the current. Only one cycle I am showing, that is good enough, 0, pi by 2, pi. And suppose I have started the game when there was no magnetic field present in the core. So, H as current was increasing came up to, I am so sorry, this is pi by 2 and this is pi, and this is 2 pi, correct it. And of course, the cycle repeats, only one cycle. So, it has gone like this, it has increased, then it reached B max corresponding to I max, and suppose I do not stop here, I allow the current to flow in the opposite direction, then pi to 2 pi, what is happening here, pi, and this is 3 pi by 2, is not. So, if you do that, you will see it will be like this. And I think this length should be slightly, I mean whatever is V max here, same ordinate, if you come it will come here. So, it will be somewhat like this. It will go like this, reach say minus I max. This is not correctly drawn. This is B max, I mean it goes this is suppose minus I max, this point, and then once again it will go, it will be always lagging, it is like this. See, after it is tracing the following the currents, I think this is I max. So, slight this way I should correct. This is suppose I max. This is the negative current I max. Are you getting? Not a very good diagram, but it tells you the picture. This is I max, this is minus I max. Therefore, when you are decreasing the current, current reaches 0, residual field is there. Then you further need negative current to make it 0 B, and then go on increasing the current up to minus I max, then it will reach this minus B max, this level. And after that, no looking back. So, this part, this initial part is of no consequence now, except after the first quarter. After that, as current changes, the locus of BH values will become confined here, here only. It will trace like this, go, 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 like that. So, we will continue with this because it will take some more time, but I will request you to try to go through this lecture, hysteresis thing a little bit carefully, particularly drawing this curve nicely. You will be perhaps drawing it much better, and we will next time show that the hysteresis loss per unit volume is nothing but the area enclosed by the path. That we will show, that is my target is this area enclosed, and this is called hysteresis loop, and area enclosed by BH loop is a measure of hysteresis loss per unit volume. We will continue with this next time. Thank you.